Lastly, we're going to talk about how the ideal gas law breaks down and how real gases actually behave. So, ideal gas law is assuming that we have those conditions that the kinetic molecular theory is assuming, right? Those tenets. But in the real world, the behavior of gases only works when we're dealing with high temperatures and low pressures. And you can kind of think about this. If I have a, like, let's say, gaseous water, so if I have water vapor, right? If I want to get it to condense, how do I get water vapor to condense? Well, we know that happens when it's cold. For sure, it happens when it's cold. So under low temperatures, water vapor doesn't want to be a vapor anymore. It wants to be a liquid. Same thing under high pressures. If I was to squish this guy down in its container so it's so small, now I'm forcing those molecules to start to interact with each other and combine and condense. And so when we're at high temps and we're at low pressure, we're giving it enough space for those gas particles to stay far apart. We're also giving it enough kinetic energy that the molecules, that they can bump into each other and not stick together. They're just going to bounce right off of each other. What's pretty wild is when we create high pressure conditions, such as over here in this graph, gases act pretty differently from each other. So we can see like right away, really early, so only up until about 1 atmosphere, do the ideal gas, or do these various gases act like an ideal gas, which is like laying flat on the curve. Once we get above that, things start to really deviate. Now you can see the red and the orange stay pretty close. So nitrogen and it looks like hydrogen stay pretty close for a bit before they deviate. But carbon dioxide and methane quickly deviate. They go down. Some of them go up. And it just depends. And this is not the level where you have to know what they're going to do. Just know that once we get higher pressures, things don't act ideal anymore. So we made some assumptions based on those tenets. One assumption we made was that that the molecules don't make up any volume. That the volume between the molecules is all of the all of the volume, and the molecules are so tiny in comparison that they don't really contribute. But this breaks down when we have high pressure. Once we squish them down and we take away all of the space, so now they're just stuck in this really tiny space, now the molecules their volume really does start to matter because there's not as much space in between them. So that is one where that breaks down. The other one that we talk about is attractive forces. We said that there's no attractive or repulsive forces between gas molecules, meaning that when they bounce into each other, they just bounce right off. They don't stick together. They don't repel. They just kind of neutrally bounce off. This breaks down under low temperatures. Under low temperatures, we have a thing here. Under low temperatures, the gas particles aren't moving very fast, and so they have more of an opportunity that when they bounce into each other, they might feel some forces. They might stick together and not bounce straight off. And so low temps, that's when our gases start to condense because they start to stick together. So a really fun, quote unquote fun, correction for real gases under higher pressures and lower temperatures gets taken into account in the van der Waals equation. There are two adjustments that get made. First one, the pressure adjustment gets made due to the fact that the molecules do attract and repel each other, really attract each other under low temperatures. And so because of that, the pressure of the system is going to decrease. So if I have a gas, right, and I'm assuming ideal gas law, then there's going to be all of the gas particles crashing into the surface. When I have some molecules that under low temps, they are attracting to each other, some of them are going to condense at the bottom, forming like a liquid. And so I'm going to have less molecules in the gas phase that are creating pressure. And so we have to, due to the attractive repulsive forces, we have to correct for this pressure, the fact that it's actually going to be lower than we would predict with ideal gas law. We also have to adjust due to the volume. We assume that the molecules under ideal gas law conditions that they don't have any volume, but this adjustment does consider the fact that the molecules do occupy some space in the container and have their own volume, and so we need to take that into account. So the overall equation is, for the van der Waals equation, instead of just PV equals nRT, we have this pressure piece where we're going to add n squared times A over V squared. So where A here is a coefficient based off of the molecule. So you could look that up. So this is that pressure adjustment. We're going to have the volume adjustment where we're going to have volume minus NB, N being the moles, equals nRT. So N or B and A are both just coefficients related to the gas. There are tables where you can look that up for each molecule and then plug those in under some of these non-ideal conditions. But luckily for you, we're not going to use these. I just want you to conceptually understand that when I have low temperatures, the repulsive or attractive forces start to kick in. When I have high pressure, now I'm squishing them together, their volume does start to matter. So just understanding the concept is all you need to do. You will not need to plug into van der Waals equation.